Hello, my name is Loaiza-Ganem, and I will tell you about our July 2022 TMLR paper, Diagnosing and Fixing Manifold Overfitting in Deep Generative Models. Before I start, I will just preface this by saying that this is meant as a summary. So if you are curious about any details and want to get into the nitty-gritty, please do check out our paper, which is linked in the description.
This is joint work with my colleagues, Brendan Ross, Jesse Creswell, and Anthony Catarini. In our paper, we assume access to IID samples of data coming from some distribution P-star and high-dimensional ambient space, whose dimension we denote as uppercase D, and the task at hand is to use the samples to learn P-star. Likelihood-based, or explicit, models, such as variational autoencoders, or variants like adversarial variational Bayes, energy-based models, normalizing flows, and continuous autoregressive models all tackle this problem. While their inner workings vary, they all use neural networks to construct an uppercase D-dimensional density, which is then trained by maximum likelihood or some lower bound of it. Now, ambient space is assumed high-dimensional, so this construction contradicts the manifold hypothesis, which states that the data actually lies on a lower dimensional manifold of dimension lowercase d, embedded in ambient space. This is a modeling mismatch, and the question motivating our paper is to gain an understanding of this mismatch, if it is relevant, and if it causes any issues, how to fix them. Before answering this question, I want to emphasize its importance by talking about the manifold hypothesis and maximum likelihood, and why they are relevant. There are many reasons to believe in the manifold hypothesis. For example, deep learning recovers low-dimensional representations of data, and would not be as successful if there was no low-dimensional structure in the first place. There is also empirical evidence, where the intrinsic dimension, lowercase d, of commonly used image datasets has been estimated, and observed to be much lower than the dimension of ambient space, uppercase d. And there are also theoretical reasons to believe in the manifold hypothesis. For example, kernel density estimation has exponential sample complexity on the intrinsic dimension of the data. So, if this dimension was equal to uppercase d, the problem of learning distributions would essentially be impossible in practice. Yet as a field, we have developed algorithms that work well, despite some problems that I will outline later. The mere success of deep generative models is yet again evidence supporting the manifold hypothesis. To further motivate the relevance of studying the dimensionality mismatch between the data-generating distribution and likelihood-based models, let's think about maximum likelihood for a second. Maximum likelihood is unarguably one of the most important concepts in statistics and machine learning. It has been thoroughly studied, and we understand it well. We know that, under assumptions that look reasonable, it has nice theoretical properties, such as consistency and asymptotic efficiency. Importantly, though, one of these assumptions is the existence of a ground truth density. And while this was indeed a reasonable assumption when the theory was developed, it cannot possibly hold under the manifold hypothesis, which, as previously mentioned, is how we should think of high-dimensional data. In spite of the assumptions not holding, we nonetheless tend to think that maximum likelihood is a principled way of training deep generative models. In our work, we argue this is not the case. We argue that training flexible full-dimensional density models when the data lies on a low-dimensional manifold results in pathological behavior which we call manifold overfitting, of which I will now give an example. Let us consider a very simple case where ambient space is one-dimensional and the manifold is zero-dimensional, consisting only of 2 points, -1 and 1. And let's also assume that the data-generating distribution assigns probability 0.3 to -1 and 0.7 to 1. Now, consider feeding a one-dimensional Gaussian mixture with two components to this data. This model is parameterized by a mixture weight lambda, means M1 and M2, and a shared variance sigma squared. In this example, we will think of this model as a flexible density approximator. In order for this model to recover the ground truth distribution, the model would have to correctly set the means, set the mixture weight properly to 0.3 or 0.7, depending on how the means were set, and send the variance to 0. Let's think through what happens in this case, and whether this has to happen or not. This video shows what happens as the variance is sent to 0, while the means and mixture weight are specified as I just described. Clearly, this results in likelihoods diverging to infinity, which obviously maximizes the likelihood. The fact that the likelihood becomes infinite is not really a problem, though, since the target distribution would essentially be recovered. However, the likelihood can be maximized otherwise. For example, this video now shows the same models as the variance is sent to 0, except the mixture weight was changed to assign probability 0.8 to -1. The likelihood is also essentially maximized here, since it goes to infinity, but the model recovers an incorrect distribution on the manifold, namely the one that assigns probability 0.8 to -1 and 0.2 to 1. This example provides the intuition behind manifold overfitting. As long as the model concentrates its density around the manifold and spikes around it, the likelihood can be made arbitrarily large, while nonetheless recovering a wrong distribution on the manifold, rather than the data-generating distribution P-star. This figure summarizes the discussion, showing both the intended behavior recovering the ground truth distribution with the orange dashed line, and manifold overfitting, recovering an incorrect distribution on the manifold with the purple dotted line. We also show the result of training a VAE in blue, and we can see that while it assigns some probability between -1 and 1 due to limited capacity, it does not assign the correct probabilities to -1 and 1, namely 0.3 and 0.7. Even if we were to quantize. In other words, the VAE is overfitting to the manifold. Now, you might be tempted to think that the previous example is special because the manifold is zero-dimensional, or in other words, the data is discrete. However, this is not the case. This video shows the exact same phenomenon happening, this time with ambient dimension 2 and intrinsic dimension 1. We can see the two-dimensional density spiking around the manifold, which will result in arbitrarily large likelihoods diverging to infinity, while nonetheless recovering a distribution which would assign higher probability to the incorrect regions of the manifold, in this case the left, rather than the right as done by P star. Once again, we can see manifold overfitting happening in practice. This example shows a different likelihood-based model, this time an energy-based model, correctly learning the manifold by concentrating mass around it, but doing so in an incorrect way. The model assigns more density to the upper part of the circle instead of the right part of it as it should. So, why does manifold overfitting happen? Since the manifold is infinitely thin in ambient space, it has Lebesgue measure 0, it is possible to send densities to infinity along the entire manifold without violating the requirement of the density integrating to 1. This would clearly be impossible if the dimension of the model was correctly matched to that of P star, and this is also why manifold overfitting happens. Know that manifold overfitting is a very general problem and will affect any high-dimensional model based on maximizing likelihoods. So far, we have developed intuition about manifold overfitting and why we should expect it to happen. But can we formalize this intuition? The answer is yes, and we show that essentially any distribution P dagger on the manifold can be recovered with densities diverging to infinity on the entire manifold. This means that, if the data we observe comes from P star, maximum likelihood can in principle recover any arbitrary distribution P dagger on the manifold. P star need not be recovered. If you want to see more details, please see our paper. There are some natural questions about manifold overfitting that you might be thinking about, which I will now answer. First, you might be wondering if I am somehow implying that the theory of maximum likelihood is just wrong. This is not the case. I am simply saying that it does not apply in our setting, and manifold overfitting elucidates why. You might also recall that maximum likelihood is often justified as being equivalent to minimizing the KL divergence of P star against the model, and so you might still not be convinced that manifold overfitting is not contradictory to the well-known theory of maximum likelihood. Once again, though, this is not the case. When P star is supported on a low-dimensional manifold and the model is full-dimensional, the KL divergence is always infinite, and minimizing it is not equivalent to maximizing the likelihood of the model. You might also be wondering if manifold overfitting is just regular overfitting in disguise. The answer is again no. Regular overfitting is caused by memorizing data points, and manifold overfitting is not. In particular, this makes manifold overfitting persist even if we were to observe an infinitely large dataset, unlike regular overfitting, and it also makes manifold overfitting harder to detect in practice. Finally, there is a question of what happens if the data is just very close to a manifold while being fully dimensional, rather than lying exactly on a manifold. For example, can we add a bit of Gaussian noise to the data and then use maximum likelihood as usual? While this would theoretically indeed prevent manifold overfitting, in practice, the target distribution being very peaked around a manifold means that large, albeit not infinite, likelihoods can still be achieved just by concentrating density around the manifold. I will come back to this point when discussing our experiments, where we show that manifold overfitting can indeed still happen if Gaussian noise is added to the data. At this point, I have hopefully convinced you that manifold overfitting is a relevant problem affecting likelihood-based deep generative models. So, how do we fix it? Well, since manifold overfitting is caused by mismatched dimensionalities, why not try to remove this mismatch? Deep learning has been tremendously successful at recovering low-dimensional representations of data, so why not reduce the dimension of the data first, and then use maximum likelihood on the low-dimensional representations? This figure exemplifies our proposed two-step models, where in the first step we train an encoder lowercase g and a decoder uppercase g, so as to obtain a dataset of low-dimensional representations. In the second step, we train a likelihood-based deep generative model on this low-dimensional data. Importantly, the first step removes the dimensionality mismatch, so that maximum likelihood does not fail when applied during the second step. The final model is then given by pushing forward the density from the second step through the decoder uppercase g from the first step. That is, if we want to sample from the model, we just have to sample from the low-dimensional model and then run that sample forward through uppercase g. Just as we formalized manifold overfitting, we also formalized two-step models as a solution. Once again, I refer viewers interested in mathematical details to our paper, but essentially this theorem shows that if the encoder-decoder pair managed to reconstruct the data, then learning the distribution of the low-dimensional representations and mapping the result through the decoder uppercase g indeed recovers P star. The theorem also shows that maximum likelihood is a valid way of learning the low-dimensional distribution, meaning that manifold overfitting is avoided. The theorem has another unexpected but very pleasing consequence. It enables density evaluation of trained two-step models. One has to be careful with how this density is defined, as it only holds on the manifold, but we can evaluate it. This consequence is relevant because of the following observation. The quote-unquote decoder and encoder need not be trained with an actual autoencoder. Many deep generative models have encoders and decoders themselves. For example, VAEs, adversarial variational Bayes, Wasserstein autoencoders, and bidirectional GANs. We could even think of a regular GAN as having a decoder uppercase G, that is its generator, and then the encoder lowercase g could be trained afterwards through any GAN inversion technique. These last examples are particularly interesting, as WAEs, BiGANs, and GANs are all implicit models for which density evaluation was previously unavailable. The two-step correctness theorem then tells us that, as long as we have an encoder and train a likelihood-based model on the low-dimensional representations, we can actually do density evaluation on these implicit models. The final observation here is that any encoder-decoder pair and low-dimensional density model forms a valid two-step model. As it so happens, several such models have been proposed before in the literature and observed to work well. Our theorem thus provides a theoretical justification for all these models. I will now talk about some of our experiments, starting with a sanity check. Consider the example I showed earlier, where a two-dimensional energy-based model exhibited manifold overfitting and failed to recover its target one-dimensional distribution. In contrast, a two-step model where an autoencoder first recovers one-dimensional representations, over which the EBM is trained on the second step, not only properly recovers the manifold, but also the distribution on it. We also compare two-step models against standard single-step models trained via maximum likelihood on several image datasets. VAEs and adversarial variational Bayes provide a great basis for comparison, as they encode and decode but are also likelihood-based models. We can see that, regardless of the choice of second-step model, two-step training consistently outperforms maximum likelihood. These results hold even when taking into account the fact that second-step models require additional parameters by comparing against bigger baseline models. And as I had previously mentioned, the results also hold even when Gaussian noise is added to the data, showing that manifold overfitting remains a practical issue even when the data is just close to a manifold. It is also worth noting that we tuned the amount of noise being added to these baselines, but did not tune our two-step models. Our manuscript shows more comparisons, and I show some samples here. The first row displays samples of standard models trained through maximum likelihood, and the second row shows competing two-step models. The improvement is obvious. Finally, we also carry out experiments to verify the usefulness of having endowed implicit models with density evaluation. A known failure mode of likelihood-based methods is that they sometimes assign higher likelihoods to out-of-distribution, OOD, data than they do to in-distribution data. For example, models trained on fashion MNIST assign bigger likelihoods to MNIST than they do to fashion MNIST, and the same happens with CFAR10 and Street View house numbers. This table shows classification accuracy of a decision stump, which tries to differentiate between OOD and in-distribution data using only likelihoods. The classifier is forced to assign large likelihoods as in-distribution, so that accuracies below 50% indicate the model assigns bigger likelihoods to OOD data. We can see that once again, two-step models outperform models trained with maximum likelihood. Importantly though, these two-step models use implicit models for the encoder-decoder pairs, and so these results highlight the usefulness of density evaluation enabled thanks to the two-step correctness theorem. In conclusion, our paper studies manifold overfitting, the pathological behavior that arises when using maximum likelihood to train a full-dimensional density to model data on a low-dimensional manifold. And we propose to fix manifold overfitting through two-step models. In addition to addressing manifold overfitting, two-step models enable density evaluation on implicit models and theoretically justify a large class of existing models. Thanks for listening. I hope you found this interesting and that you will be aware of manifold overfitting and how to avoid it the next time you train a deep generative model.